So I'm not speeding through it, but I do want to make sure I'm just trying to save our review time. Some of this stuff is basic, except for the Rybert equation. So this is the last slide of notes that was not covered. So we're gonna mess with this. We're gonna deal with this a lot in the lab. But write down what you need to. The spectrum come in 3 varieties. Spectrum is just a version. So we're going to see these spectra momentarily. The ones that we're really going to be able to see are the bright line spectrum, the bright line emissions. What are the emissions caused by? Who's got me here? What's causing this light emission? But where are the light waves coming from? Electrons doing what? So dropping down, specifically from the emission, right? So specifically electrons dropping energy levels. That's what's causing this light spectra. But it has to emit a specific amount of energy for it to fall in the visible light wavelength so we can see it. Some of these energy drops are not going to fall in the visible light spectrum. They're going to fall either on the more energetic side, UV, or the less energetic side, IR. And we won't be able to see that, but we could detect them in different ways. But we're going to deal with ones we can see. The sun gives off a continuous spectrum, meaning there is no gap. It has every wavelength of the known universe. So there's a white light spectrum. There's no gaps. There's no black spots there. The bright lines are going to be the ones like this with the black background and the emissions at various wavelengths. And these are going to be unique to individual elements because every element has a different number of electrons, a different number of drops that will occur, therefore a different number of lines on the spectra. So it's called the atomic fingerprint. You good so far? Okay, so everything here is going to be kind of leading into the modern model, which is the quantum mechanical model. So we have Bohr, Schrödinger, de Broglie, Heisenberg, Planck, Maxwell, Einstein, a lot of scientists that helped develop the quantum mechanical model, but we're going to really relate the quantum mechanical model more to electron configurations than necessarily light. So a couple more things. We just talked about this. Because this whole energy level system exists.
We will not have bells this morning for a time. Please follow your time on your computer for your schedule. Thank you.
Okay, because in the Bohr model suggests that there are set pathways for the electrons. That set pathway has a set amount of energy, and since they have a set amount of energy, there's a set amount of energy that can exist when the electron drops. So we call that quantized. We just have a term for it. That's an easy question to get right on multiple choice if you know what the word quantized means. Other than that, how do we get to this equation? Basically, the ones that we're actually looking at is this one, okay? There are two equations. C is equal to wavelength times frequency. Energy is equal to HV. What is H? Which is
0.62 seconds times 10 to the 34 joules seconds.
34. What are the units? Joule seconds, right? Joule seconds. And then what is the speed of light? 3 times 10 to the 8th meters per second, right? C is equal to 3 times 10 to the 8th meters per second. You should be able to manipulate these two equations by putting them together. E is equal to hc over lambda, lambda being wavelength. You can always flip those, which is what we're going to do a lot of times, actually solve for the wavelength of a specific amount of energy. All right. So, and all this exists, all this just relates to the Bohr model. Bohr model is specifically for hydrogen. It does not work for any other atom, but it was useful for us to actually learn more about spectra and about how different other atoms emit their energy. This is all related to Bohr model. Fixed distances, so that's our set pathways for the energy level where the electron can exist, and that's going to give off certain amounts of energy. How does this contrast with the quantum mechanical model? From your reading. Bohr said there's set pathways. Try. Okay, so quantum mechanical model, the clouds are called, so Bohr called these concentric circles, orbits, what does the quantum mechanical model refer to them as? Orbitals, right? We got real crafty. Orbitals versus orbits. And orbitals are a likely place where we will find electrons. It's not certain because we can only know one larger characteristic about the electron, either its speed or its location. And so I don't know if I told this in the video, I don't think I did. So Heisenberg and Einstein were going down the road. Whoop, whoop. They hear a police car. They pull over. This man goes, shh. Whoop, whoop. He said, "Sir, do you know how fast you were going?" He said, "No, 105 miles an hour." They're like, "Dang it, now we're lost." Only you guys will get it. You can either know how fast or where you are. Milers are like, okay. Okay, so that's the differences there are that the orbitals have different shapes and they don't have set pathways. They also have a likelihood of finding an electron. We say that they definitely will find the electron in these specific shapes. What are the shapes of the orbitals? What does the s orbital look like? Circle. What does the p orbital look like? Dumbbell. Dumbbell. Okay. D orbital. Double dumbbell. So S looks like a sphere. P looks like a dumbbell. D looks like a double dumbbell. And F looks like a flower. F. Okay? Perfect. Perfect. You need to know the general shapes of those. You don't have to draw the F one. It looks horrible. There are more images of this. Okay, so another fact about the spectra are sometimes we're going to have different amounts of energy released, like I said, relating to visible, UV, or IR. There are actually people who figured out a lot more information about this, so they named these things after themselves. The series are referred to as the Lyman series, the Balmer series, and the Paschen series. I have on the bottom how you can memorize them. So the different drops relate to, it doesn't matter where you start, it's where you end, where your final drop is to. And you'll notice that there's a large amount of energy between, oh look, this one's a little easier to see, between energy level 2 and energy level 1. That's lots of energy. I don't know what those two S's there. Okay. So anything that drops from a high energy level down to energy level 1 is called, or is a wavelength, or a wavelength within the Lyman series. Anything that drops to energy level 2 is the Balmer series. Anything that drops to energy level 3 is the Paschen series. This is how I've remembered it since I was your age. Lyman drops to the lowest. Write this part down because you need to know which is part of which series. The Lyman series drops to the lowest energy level, which is energy level 1. And since it's dropping through that huge gap from energy level 2 to energy level 1, that's a lot of energy. And the most energetic form of energy is gamma. But we're not that far. There's not that much energy being released. So UV is the most energetic of our little sequence we're looking at. So Lyman low is how I remember that. I have to come up with these little cheesy ways to remember things. The Balmer series is anything that drops from a high energy level down to energy level 2. So if you think of Balmer as bi means 2. Think of it like that. I think that will hopefully help you remember that's dropping to the second energy level. And since that's a mediocre amount of energy, we're going to put that in the middle of the spectrum, which is the visible light. So most of the light that we see is due to some drop in energy that's in the Balmer series. Paschen is going to be dropping to n equals 3, which is not a big drop. If you're starting at a high energy level like 4, 5, 6, 7, and you drop to 3, there's not a lot of energy there. So not a lot of energy means IR, which is a low energy wavelength, and a low energy wavelength is kind of what's referred to there. So I remember, in organic, we have like propylene, propanol, propane. Prop means 3 carbons. Yes, you remember this? Okay, that's how I remember. Paschen is like prop, which is n equals 3. You can make up your own if you want, but that's what I've got for you. Okay. Okay. So these are just series of wavelengths or energy that's released as an electron drops from a high energy level to a specific secondary level. Okay, now we're going to do Rydberg. Yes. Okay. Do you remember seeing something like this in your reading? Okay. Do you remember, how about like, well, I'll write it again up here for you in a second. So the Rydberg equation is going to actually quantify that energy loss, not just saying from n equals 2 to 3 or from, whatever to whatever. It actually quantifies it by calculating the energy difference based on the constant. You need to know the constant, the RH constant, which is the Rydberg constant, is 2.178 times 10 to the negative 18 joules. And then that is actually simply written as this. Written in this form, this actually gives you the energy in an energy level. And we are not always concerned about the energy just in that energy level. We're actually more concerned about the differences in energy between two energy levels. Because that difference in energy is either given off, being, emissive. We can see it as light, like visible light, or that energy is actually given to the electron to make it jump up to a higher energy level. So it depends if we're asking for a specific energy level or a difference. More often we're looking for a difference. So each of these terms are defined specifically. This is only true, this Rydberg equation is only used for hydrogen. So do you guys remember the Z number is the atomic number? If you don't know, you do. The Z number is the atomic number. That is for hydrogen is 1. So that number up top is always 1. And then the N number is the energy level that we're speaking of. So if I'm talking about the first energy level, then I'll also have 1 there. If I'm talking about the second energy level, I'll have a 2 there. So what we're going to do is actually compare them. And I will write this on the second page. We look at the comparatively two different energy levels we look at the two different energy levels to calculate the energy difference between them. So the change in energy is equal to the negative RH value times 1 over N final squared minus 1 over N initial squared. That is the equation you will use extensively. You'll use that in your lab today too. So let's say, what's next on here? Look at number 52 on your little page, page 3 in your packet. Question number 52. And I'll go back to the slide with the information for you in just a second. So 52A says, calculate the wavelength of light emitted when each of the following energy transitions, or each of the transitions occur for the hydrogen atom. What type of electromagnetic radiation is emitted? So, is that 52? Yeah. So what we want to do first, let's calculate the energy first, and then I'll show you how to calculate wavelength, but then I'll show you how to compare them together. So what is the RH value? You wrote it down. What's the RH value? Negative 2.18178 times 10 to the negative 18 joules. Okay, so that's the constant. And then what is the N final for number part A? What is the final energy level? 3, because it says from energy level 4 to 3. Is that what it says? A? I'm on A. Okay, it says this, right? 4 to 3. So energy level 3 is our final, so we'll do 3 squared minus 1 over our initial of 4 squared. So can you tell me right now before you calculate, is this going to be a negative or a positive number, meaning is energy released or absorbed? Look at the transition. Look at the transition. It's dropping, right? So is energy released or absorbed? Released, and you represent that by a negative E. Okay, released means, or negative energy means energy is released, and you can look at it to see that, is this going to be a larger number or is this going to be a larger number? 1 over 3 squared is a larger number than 1 over 4 squared. So you're going to have a large number minus a small number times a negative value. That negative reigns, and so the end energy is also negative. So calculate this for me. You guys have your calculators? I want you to plug this one in because I want to make sure you're plugging in correctly. I love you and stuff, but we had really stupid calculation errors on our electric test. There weren't that very many calculations, so you were really crafty in your calculations. Crafty is my word for today. Oh, I have to finish reading the extra credit when I'm done. Yeah. right, answer. Anybody? Tell me the answer. Negative. So I'm gonna round, okay, 159 maybe, times 10 to the negative 19 joules. Okay, this is the energy of the photon that is released. Okay, the question was not asking about energy, it was asking about, okay, question again? Okay, it's asking about what type of radiation and the wavelength, right? So how are we going to manipulate and find wavelength? You maybe wrote this equation down last night in reading or in your video. How do I manipulate? How do I get energy, or sorry, wavelength from energy? I have to use Planck's constant. Give me the whole equation together. So we just said E photon is equal to. Okay, this is the combined equation of C is equal to lambda times frequency and energy is equal to Planck's constant times frequency. So instead of writing 2 and then finding them, again, know that, just know it. But you can easily take the two constant, or the energy and the wavelength and flip them. So morphing it into wavelength is equal to hc over E. So that's the one that we are going to use to calculate right now the wavelength. So what I can do is just take this energy, pop it on the bottom, hc are constants, multiply your two constants, divide by your energy, tell me what your wavelength is. I'll write the work up here, but you guys start calculating. Oh, and then note that that negative, what does this negative here mean again? Up here. What was it signaling? Energy was released. That is not included in our E because wavelengths can't be negative. There's no such thing as negative length. So we'll just put the positive, our absolute value of this down here. And then, ready when you are? Hold on, what did I just say about the negative? 1.88 times 10 to the negative 6 units. Look at my units and cancel them out. Meters, thank you. So that's our wavelength in meters. Now, can you tell me which form of wave that is? Is it longer? Oh, okay. So if visible, I need you to know that visible light is between 400 nanometers and 700 nanometers. This is violet light. This is red light. So is that going to be closer to? Hold on, before I do that, can you convert nanometers to meters in your head? Do you remember how to had a nanometer? Okay. So it's always going to be. Most of the time, visible light is times 10 to the negative 7th because 400 nanometers times 1 meter is 10 to the 9th nanometers. This is your metric conversion. Nano 9, remember that, to the 9th power. So 400 divided by 10 to the 9th is 4 times 10 to the negative 7th meters. That's violet. So then you can assume, quantitatively again, 7.0 times 10 to the negative 7th meters is red. So, is this guy that we calculated longer or shorter than visible light?
Longer.
Longer, because this is 10 to the negative 7th, this is 10 to the negative 6th. What is a longer wavelength? Infrared. So this is an infrared one. It's right on the other side of visible, so it's not very far away, so you're going to go with infrared. Longer means more energetic or less energetic? Less energetic, so also the frequency is lower. Usually your indirect and direct relationships. So, guys, how could we actually minimize our work here if the question simply said find the wavelength? Can you combine any steps? Right, we know this, right? We know that this is what we're shooting for. I can just go ahead here, H times C over this whole thing down here. If you're good with your parentheses and your calculator. And I think you can do that together. If not, doing two separate steps. But that's how you use the Rydberg equation. Okay? Okay, so I think I got one more type of question for you. Did I tell you everything here? Yes, light, energy, hydrogen, energy final. We know that the values are just telling us if the energy is being released or absorbed. Yes. For weight, you don't have to use linear calculations of weight. You do show the negative if it's asking for the energy. Yep. Okay, we just did that. And we're not going to the right now. Okay, let's do our lab. Nice. I told myself I wanted 20 minutes on that first. We'll do some checks performance after you get back from your lab, okay? So, lab is the second to last page in your packet. I want you guys to practice some more of this Radbird before I start doing homework. The spectroscope. Second one page. Spectroscopes are around. You know how to look at these? Maybe you got maybe some years. The little, if there is an emblem on yours, the emblem goes on top. The little tiny hole, which is where the light enters, points at the light source, and I'm going to have the hydrogen emission tube lit up over here in the gas just for 2 seconds. So you're just going to point this at the light source. There's a diffraction grating on this side. When you look into the light, you'll see bands, and those bands are not wavelength, nor are they angstroms. Look at the top of your reading. The light is down. It says procedure, number 1. So each of these lines represent how many angstroms? 1,000 angstroms. And you need to convert from angstroms to meters. And then you'll have to convert to energy. So this will take, I'm going to say maybe 30 minutes to get all your data, and you guys start calculating. This is kind of a practice lab more than like experiment lab. Okay, so form your own groups. Let's do groups of 3. Come back here. You will need your calculator. Oh, and let's say, I want you to ask somebody you've never worked with before. One person in your group that's never been in your group before. Can you 2 people that are together? I want you guys to choose. If not, I can choose. So I'm leaving it to you guys.
You'll never be one of us.
There's some, we'll make a combination of numbers. And then I'll have, let's see here, Maggie, Chelsea, Maggie Diamond, and Josh. They'll be there. There are 5 groups right now, guys. Okay, start reading the lab, and then I'll turn the instruction tube. It's not very long. So the hydrogen light source, I'm going to have on in less than a minute. So I'll have you guys come in names. maybe practice looking at the mercury lectures. What are the mercury lectures? Mercury, where there's a light source right in front of you and you got your station. You're going to turn yours on. Hey, blue, you got light let me turn on the little auto light here. Sorry, I just didn't know how to do that. That's a UV one you're just going you might be distorting it from my error. Alright guys, what are you looking for in the hydrogen light source? Tell me what you're looking for in the hydrogen light source. Colors, great.
Light.
Yeah? Alright, I'll let you guys figure it out. I'm gonna turn on the hydrogen light source. I'm gonna turn off the slide above me. I need the hydrogen light source is right here. You're gonna have to write down some values, so maybe send one person with a spec and one person with a paper. Okay? One person with a spec, one person with a paper. That's how you can also I mean, well, they're gonna write down some values. Alright. I can't leave it on for a long period of time. It's really hot. So, okay. We're gonna have to do like 5 o'clock. About 9. Oh, here. Let me get another light source. No, that one's red. Turn the light on the body if you hear. Tell me if this is any better. You see? You see the numbers now? Alright, what are the numbers? You see 4 lines. Okay, what colors are you seeing?
Red, yellow,
No yellow, no yellow.
red.
You see red, teal, blue.
Yeah,
Alright, keyword.
I don't know.
Okay, so somebody tell me where the red is. Guys, listen, the red's coming out. Can you tell me the number? Can I hear? I can put number. I can put 6 3/4. Can we say 6.75? 6.75 for red. Okay, next one. 4.5 for blue. Can I get aqua? So aqua's at 5 what? So 5.1. Let's go with some decimals for people. So aqua at 5.1. What? It should be a purple. Purple. Violet.
Violet one is that?
No.
No, 4.4.
4.4 sounds better. Violet, 4.4. All right, that's calculation for you guys. Start calculating. Please. I'm not crazy.
There's no blue. There's no blue.
No, it's just teal. It's gonna be like blending in black. I don't see any blue.
I also just turned off the light source that was illuminating
I can't see any.
Guessing we're eventually gonna have to.
Alright guys, I'm gonna turn the light back on. You can start calculating. I'll turn on some music for you.